All right, so hello everyone. It's good to see a lot of you back. I'm not Tim. Tim is online on Zoom because unfortunately he has COVID, so he couldn't make it today, but he was kind enough to come on to Zoom and we're going to stream that talk. Yeah, so that's it. And then so come back next week and come to the Apéro afterwards. Oh, next week is spring break, so it's not next week, it's the week after that on Wednesday, on the 27th, because the 25th is also a holiday. So it's on the 27th of April, the next talk. All right, Tim, you can take it away.
Recording in progress.
Yeah, let me start recording for you. Thank you. First of all, thank you to the organizers for inviting me today. It's really a shame I can't be there, but I'll come by for sure one of the next talks. And also thanks to the audience for coming to my talk, under the assumption that I'm not speaking in front of an empty lecture hall, but I guess that's not the case. My name is Ryck. I am a PhD student at DMath, and I will talk about mathematical guarantees for physics-informed neural networks today. So maybe I'll introduce myself first. So I did a bachelor in physics in Belgium. Then I switched to mathematics. I came to ETH, and now I'm still at ETH for the PhD. So I'm 1.5 years in right now. My supervisor is Siddharth Mishra. I guess if many of you are undergraduate students, you might not know him since he's mostly teaching in the Math and CSE Master. So he teaches a course called Advanced Numerical Methods for CSE, and also our new course, Deep Learning in Scientific Computing, which is very much related to my talk of today. Our group is called the Computational and Applied Mathematics Laboratory, and we're a part of the Seminar for Applied Mathematics. We're up in the G floor in Hage, so you might have seen it. It's right next to the math library. And we're also associated to the quite new ETH AI Center. And should you have any questions about my talk, feel free to reach out by sending me an email or something. Then about my PhD project. So I guess I work on very different smaller projects, but I would say that the overarching goal is to provide some kind of mathematical guarantees for deep learning methods that are used in scientific computing. So in our group, my colleagues, they have a lot of algorithms, a lot of methods using AI to solve differential equations, and they work very well. Often they are much faster than the conventional numerical methods. But of course, as you might have heard, these AI methods are quite often black boxes. So as mathematicians, we also want to understand why they work and when they work and what conditions we need for them. And that's kind of my goal. So I want to prove some guarantees, some error estimates for these methods. And how do I do this? Well, this is really a really fun part of my PhD project. I can use a lot of tools from very different fields within mathematics. I use tools from functional analysis, PDE theory, given that we're trying to solve PDEs, but also the classical numerical mathematics. I need to be knowledgeable about machine learning methods, but I can also use tools from statistics, like the empirical process theory course from ETH. That was also very useful for me. And because optimization is also an important part of AI, that's also something I use results from. So this is to give you a little bit of context about my PhD research and also today's talk. So I guess you all have heard about AI, about all the fantastic application this has. Like here are just some examples, like translation, automatic translation, using Google Translate or whatever, face recognition, all those recommendation algorithms from YouTube, Facebook, Spotify, and so on. They all use artificial intelligence, more specifically deep learning. What deep learning is, I'll explain a bit later. But of course, if one can see that this deep learning framework has this many great applications throughout a lot of different fields, one might also wonder, can we also use this in mathematics? And then for our group specifically, can we also use this in scientific computing? And well, turns out, yes, this really has use in scientific computing. And that's exactly what we do in our group. So one specific subfield of AI is deep learning. And in deep learning, one basically uses neural networks, a mathematical structure called neural networks, to approximate other functions. And you can see the definition of a neural network right here. It's not all too complicated, actually. So given some input vector of dimension n0 in this notation, what a neural network does is, at first, given your input vector, you apply it with a matrix and then add a vector. So this is the affine map A1. So that's the, A1 of x is equal to W1x plus B1. And then you apply some activation function rho. This is usually a nonlinear function, and you apply it element-wise to this vector. So then you get a new vector with the same dimension as before applying the activation function. And then you apply another affine linear map, and then you apply another activation function. And you repeat this process L times. And also note that the dimensions of like all these NL, they don't have to be the same. They can be different. So a neural network is basically just a concatenation of affine linear maps on the one hand and of activation functions that are applied element-wise or entry-wise on the other hand. So it's quite a simple structure. And how can they be used to approximate functions? Well, one can, of course, choose the entries of these weight matrices W and the bias vectors B. So in choosing those entries, one can change the neural network, one can change the output, and the goal is to choose the weights and biases in such a way that's a good approximation of the function you want to approximate. And this is then called training the neural network. Why are they called networks? Well, if you visualize the computational graph of this function below, then it kind of has some network structure. So if you look at the figure on the left, you start with an input vector of dimension 4. You see the blue 4 circles there. And then you apply an affine linear maps that goes from R4 to R6. And then you end up in this first column, let's say, with the 6 black dots. And those then represent your values after this affine mapping and after this application of the activation function. Then you have a vector in R6. And then all the lines in between, they basically represent all the weights. So all the entries of the matrix W1. And then one can see that this A2 affine mapping maps from R6 to R6. And then finally A3 will map from R6 to R2. So in total, we will say that we have one input layer on the left, one output layer on the right, and then 2 hidden layers in between. That's just the common terminology. And we also say, like it's right here below, that the depth of the network is L. So the depth of the network is equal to the number of affine maps. And then the width of the network is just your maximum dimension in the hidden layers. And then the total number of neurons basically is just the total number of circles you can see in this graph here. Then one other thing I want to mention is you, of course, have to choose this activation function rho. In practice, there are a lot of possible choices. The one choice we will focus on in this talk is that of the 10H neural network. That means that you just use the hyperbolic tangent function as activation function. And then, as I said before, you apply it element-wise. Okay, so this is the setting for my talk. Of course, as I said, the goal is that we will approximate solutions to PDEs with these neural networks. So we want to approximate functions, so we need to be able to quantify the error that this neural network makes. And for this, we need norms. So depending on which year you're in, this is either very easy or maybe you just learned it. So I thought I would just make a slide to repeat this. So the most common norm is, I guess, the C0 norm, which is just different notation for the subnorm. So you just calculate the maximum value that f minus g in absolute value has. Then some generalization would be the CK norm. So instead of only looking at f and g, you also want that the derivatives of f and g are good approximations of each other. So you will look up to the kth derivative in this case. So if f minus g is small in CK norm, then this means that up to the kth derivative of f will be a good approximation for the, well, up to kth derivative of g. And then for PDEs, we will also often look at the L2 norm. This is just some squared average of the error over the whole domain. Yeah, so we take the integral instead of calculating the maximum, and we will approximate solutions to both ordinary differential equations. This is just an example I took from the analysis 1 or 2 lecture notes, so you should definitely recognize it for the first year students in the audience. And then we will also look at partial differential equations, meaning that there are multiple variables. So this is quite applicable in general to a lot of PDEs, but I will just focus on the heat equation in this talk because it's very easy and I really want to focus on the concepts rather than the mathematical calculations. Okay. So what is the central question in this talk, or one of the central questions in this talk? That is this question asked by people that are occupied with neural network approximation theory. So given some function class f, function class being, for example, k times continuously differentiable functions, and given an arbitrary function in this function class, we want to know what size a neural network should have such that f minus f hat being a neural network, is small in some chosen norm. Right? This is exactly what happens in practice. You have some function you want to approximate. You don't know what the function is, but you do know some properties of the function. You don't know in which class the function is. And then you need to know how big your network should be. You need to know the depth, you need to know the width, such that you can sort of initialize this architecture, and then you will find the weights and biases that can approximate this function. And you can find these weights and biases by training the network using stochastic gradient descent, for example. But for this, you first need to know how big the neural network should be. So this is really a very important question. And a typical result, this one is inspired by Jarodsky, would say, well, given some accuracy epsilon and then some k times differentiable function on the d-dimensional unit cube, there exists a 10H neural network with this many neurons. So convergence rate is epsilon to the minus d over k, such that the error is smaller than epsilon. Now, what do we see here? First of all, we see that when the input dimension is higher, so when d is big, then this convergence rate gets worse, meaning that you need more neurons if the input dimension is bigger. I guess that's quite, quite intuitive, because your function is harder if you have more, a bigger input space. On the other hand, if your function is smoother, if you have more regularity, then you will need relatively less neurons. Right, so these are already quite important observations. So how would we prove this? Well, that's really the cool thing about these neural networks. they really allow for constructive proofs. So you don't really need to show that there exists some neural network. We can actually construct an exact neural network with just our bare hands, with just the basic mathematical tools. Some simple properties, well, simple if you think about it a bit, are that a sum or a composition of neural networks are again neural networks, right? That's because, for example, for the composition, the beginning and the end of a neural network is in a affine linear map. And if you, compose two affine linear maps, you will still get an affine linear map. So that is how it will still be a neural network. And then, for instance, for the ReLU activation function, ReLU stands for rectified linear unit. That's because, well, this is the definition. So you have, for positive x, it's the same as a linear function, but for negative x, it's just 0. So it's rectified is what they call it. So with this definition, one can see that you can just exactly obtain the identity mapping with this ReLU function. You just do ReLU of x minus ReLU of minus x, and you exactly get the identity mapping. And the same thing with the maximum of two numbers. You can also exactly represent this. And then you can think of, okay, how can I represent an approximation to a function, for instance, with Taylor polynomials? And then you can use expressions like this to define your neural network approximation. For smooth activation functions, on the other hand, such as the hyperbolic tangent function we're looking at in this talk, you can do something like this. So what you see here is basically a Taylor approximation of this one here, of the derivative of sigma in 0, and then you divide by some terms. You need to rearrange some stuff. But basically, what this says is that you have a second order approximation of x if you use this expression. And this expression, again, fits in the definition of a neural network. You can see that this is a neural network with one hidden layer, because what we have here, right, your x is your input, you multiply by h. So this h will go into your weight factor. And then you multiply by 1 over 2h sigma prime 0. And then for the other one, you multiply by minus 1 over 2h sigma prime in 0. And then you add both of them. So this is a very small neural network, but it's a second order approximation of the identity function. And this is, again, something we can use in our proofs later on. Okay, but now let's come to the essence. Let's go to PDEs, because we want to solve these PDEs with neural networks. Of course, the first question one might ask is, why do we even want to do this? Don't we already have enough classical numerical methods to do so? And the thing is, yes, we have classical numerical methods that in theory work very well, and also in practice they work well, but they can be very expensive. In particular, for high dimensional functions with a lot of parameters, or if you want to do something for uncertainty quantification, this will become too expensive in practice. A very good example is the model of some model for shallow water equations. And it basically says that if you have an earthquake underwater in, say, the Mediterranean, and you want to calculate how the water will propagate to check whether there will be a tsunami somewhere, or how high the waves will be when this propagated waves will reach the coastline, you need to solve a very complicated model. Of course, when there's an earthquake and a tsunami might be coming, you don't have a lot of time. And if you use the current numerical methods, the calculation might take longer than the time you have before the tsunami hits the coastline. Whereas with these neural networks, it might take a very long time to find the right neural network, but once you have it, you can evaluate it in seconds. So it would be much faster. And that is why we are interested in using neural networks to approximate solutions to these PDEs. Okay, so let's go over our setting here. So we have a domain D. Then we have some differential operator that maps between some function spaces, Banach spaces, usually Sobolev spaces for the advanced undergraduates. So in the case of the heat equation, that's just this operator. And then you also have some boundary operator B that just makes sure that your function satisfies the initial condition and the boundary condition. So in this case, you want that your function at time 0 is equal to the prescribed initial condition, u0. And then what we will assume is that there exists a classical solution. So u will be our classical solution to the PDE. So in this case, u satisfies the heat equation, and u also satisfies the initial condition. Of course, one might also look at weak solutions because these classical solutions don't need to be defined for every PDE. But I mean, this is a bit out of scope for this talk. So we'll just look at classical solutions. And then the goal will be to approximate u with a neural network such that u minus u hat is small in L2 error. Now, there are two different methods to do so. The first one is sort of the vanilla, the usual simple method, and this one uses supervised learning. Supervised learning is something that has been around in AI for a very long time. The best way to think of it is with image classification, for example. You just give your computer a bunch of pictures, and you say for each picture, okay, on this picture there's a cat, on this picture there's a dog, and so on. So you supervise the learning process because for every picture you give, you say what the correct label is. And then the hope is that if you give it a new picture, the computer will determine the correct label itself. So in the setting of solutions to PDEs, you need to select some grid points and use a classical PDE solver. So you have to use the conventional numerical mathematical methods to approximate the solution in these grid points. Yeah, so usually you will do this on the coarse grid, so that's not too expensive. And then this builds your training sets. And then what you do is you try to minimize the following loss function. So you evaluate your neural network in the same grid points, and you want that the mean squared average over those grid points is small. So it's very straightforward to do. So by minimizing, I mean choosing the weights and biases in a good way, right? That's what I said before. Of course, the problem with this approach is that we still have to generate this training data. And as I said with, for instance, the tsunami example or any other high-dimensional example, this can be very expensive. So ideally, this is something we would want to avoid. And this is exactly where physics-informed learning comes in. So finally, we have reached the title of the talk, those physics-informed neural networks, or PINs, in short, as I will call them. This is where they come in. So training data generation can be expensive. And now, 20 years ago, some people had a very smart idea. They basically observed that for the true solution U, it holds that if you apply this differential operator T and the boundary operator B to U, you just get 0. So what if we just apply these operators to the neural network and then find a neural network such that D U hat and B U hat are approximately 0? Because then hopefully it's a good approximation to this true solution. So that's exactly what you do. You define these residuals, as I'll call them. Of course, you will calculate some norm of them depending on some things. And then you calculate some weighted average and you want to minimize this. So, so this has been already proposed 20 years ago. Unfortunately, they didn't really have enough computational power for that back in the days. That's why it has been reproposed by the research group of Kaniadakis and other people from Brown University a couple of years ago. And since then, it has become a very, very popular and powerful framework, because now we do have the computing power. So in this case, you still have to select some grid points, both in the domain and on the boundary of the domain. But these then will just be your training sets. You don't have to generate any training data anymore. You don't have to use your classical numerical methods anymore. And that is quite powerful, because now you can just apply the operators to the neural network, evaluate them in the grid points, then calculate some norm, and then you average. And this will be your loss function. This is what you will minimize using stochastic gradient descent or some other optimizer. So that would be a lot cheaper to do, because you don't have to use those numerical methods anymore. You don't have to generate data anymore. But of course, as mathematicians, there are some questions that pop up here. So first of all, does there even exist a neural network such that this quantity, these residuals, are small? Because we don't know this. And if there doesn't exist such a neural network, I mean, then we're screwed for this method, because, I mean, if it doesn't exist, you can't find it, and you will never be able to find a good solution or a good approximation to your solution of the PDE. And then the next question, if there exists such a neural network, how big is it? Because that's something that the practitioner also needs to know. They need to know how big the architecture should be before they can train it. So these are already very important questions. But of course, we're not interested in minimizing this residual. We want to know that the L2 error is small. And this is not guaranteed in general. We need to have some kind of stability estimate. We want to bound our orange L2 error in terms of this purple residual or pin residual. And then the last step is about generalization, because we will minimize this empirical risk version of our residual. We can't minimize this directly because, you know, in the definition of these norms, there will be some integrals, and calculating an exact integral of a neural network is very complicated in general. So that's not something you can do. So you will have to discretize like here. And then you need to hope that if this blue thing, if this blue training error is small, then the pin residual, this purple thing, will be small as well. And if so, then you combine this with 0.2, and you will also know that your L2 error will be small as well. Okay. So how can we do this? How can we answer the first question? Well, it's very simple, actually. If we know that a neural network approximates a function well in CK norm, then automatically the pin residual will be small as well. And then we have this quite general theorem here. So it says for every n and for every s times continuously differentiable function, you have a 10H neural network with only 2 hidden layers of width n to the power d, such that for every k you have this estimate. So the CK norm is going to be small, because this term here will become small if n gets bigger. And then the nice thing is that all these constants are known. They're explicitly known. And it's actually quite nice, because very often results like these are proven by computer scientists. And they usually only care about convergence rates. So they use this big O notation, and then they don't care about the constant that is implied in this big O notation. But of course, this constant can be 10 billion, and then the bound isn't really usable in practice. So that's why it's nice that we have some explicit error bounds. Okay, so let's have a look at an example. So yeah, I write here Sobolev norms. It can also be generalized from CK norms to Sobolev norms. So let's look at a very simple example. What if we want to approximate the sine function with neural networks? Well, then we find that depending on the exact value of the frequency and depending on which proof strategy you use, you need something in the order of 10 to 20 neurons in your hidden layer. And you have 2 hidden layers, or even 1 sometimes. So that's a very small neural network. That's not a big overestimate, so we're very happy with this norm. or with this estimate rather. So how would you then prove this for the heat equation? Again, this is a very simple example. For the equations we're interested in, it's a bit harder to prove it, but let's have a look at this one. So if you assume that your solution to the heat equation is S times continuously differentiable, then first you can bound the L2 error in terms of the subnorm or C0 norm. And then what we do here is we add the true solution because we know that this is exactly equal to 0. Here we apply the triangle inequality to split it up. And then this one can be upper bounded by the C1 norm of U minus U hat, and this one, of course, by the C2 norm of U minus U hat. So in total, they can be bounded by twice the C2 norm of U minus U hat. And then we get from this theorem, so if we take C2 here, we know exactly how big the network should be to get this error estimate. So this is just if you combine everything. So we get then, okay, we have that there is a neural network with 2 hidden layers and n squared neurons such that you have the following error estimates. Okay, let me have a look at time. So this is how it would look like for the Navier-Stokes equation. So it's a bit more difficult. So here you have the Navier-Stokes equation. You have different parts, and each of the parts are related to some residual. So those are on the right. And then you again have a very similar theorem. So here you have all the relevant residuals, and they can all be bounded in terms of the neural network size. So it's very similar as before. Now the only difference is that you will need a much, much larger neural network. So in this case, you need something like 50,000 neurons in our, according to our theorem, to have a 1% relative error. This sounds like a lot, but then if we look at people who did experiments, they also use neural networks, something of the order of 5,000 neurons. So it's only an overestimate by a factor of 10, which for machine learning norms is still very good. So we're still quite happy with these results. So this sort of ends the answer to question 1. Question 1 being, is there a neural network such that the residual is small? And if yes, what is the size of it? We've now answered that for both the heat equation here, also the Navier-Stokes equation here. And then we can move on to the next question. So for the second question, we want to know whether a small pin loss also implies a small L2 error. And then I'm not really going to give the details because it's just a bunch of calculations, basically, which were actually not done mostly by me, but by my colleagues. And then you can see that you can bound the squared L2 error in terms of all the relevant residuals. So this is the residual related to the divergence equation in the Navier-Stokes equation. This is related to the first line of the Navier-Stokes equations. This is the spatial boundary conditions, and this is the temporal boundary conditions, or the initial condition, in other words. And then, so that's a positive answer to our second question then. And then we want to answer, okay, does a small training error also imply a small generalization error? And unfortunately, the answer is yes again. So again, by combining the answer with the answer to the second question, we can bound the squared L2 error in terms of the training error. That's something we can calculate. This constant we can also calculate. And these are just the sizes of our training sets. These are the number of grid points. So this is a computable upper bound on the L2 error of our trained network. And that's exactly what we want to obtain. What's also interesting is that the convergence rates you can see here are different for the different parts. So you see for the interior of the domain, the convergence rate is quite bad compared to, for instance, this part here, the 2 over D. you have a much higher convergence rate for the grid points related to your initial condition. So you will need relatively more grid points in the interior domain than for the initial condition. So this already gives a heuristic before you will train the neural network for how many training points you should choose, which is also quite nice. Okay, so this is again the same error bound, and then we did some experiments. Because what we see here is that the squared generalization error sort of scales as the training error, plus then all these terms, but we will neglect them for now. So basically, the generalization error should scale as the square root of the training error. And if you look at this thing here, so on the x-axis, we have 4 orders of magnitude, whereas on the y-axis, we have 2 orders of magnitude. This is exactly the behavior we predicted from the theory. So our experiments, they really agree with our theory, which is also quite nice. Now, of course, heat equation, Navier-Stokes equation, those were all low-dimensional equations. And the problem is that all our previous estimates suffer from the curse of dimensionality. Why is this the case? Well, first of all, what does this mean, curse of dimensionality? This means that if you want to improve your accuracy by a factor of 10, you will need to increase your size by something that increases exponentially in the input dimension. So if your input dimension is very, very high, you will need a network that is very, very big. So if we go back at this theorem here, we see that you need a width of n to the power d. This is exactly this exponential behavior I mentioned before. So this is something we don't want for high dimensional PDEs. But many PDEs are in fact high dimensional. For instance, in option pricing, in the Black-Scholes model or the Heston model, the number of input variables is equal to the number of assets you want to have, the number of stocks you want to have in your portfolio. And this can be quite a lot. It's not an exception to have 100 stocks in your portfolio. So it's very clear that you can't use results like these because they will be very useless in practice. However, experiments do show that these spins can, in practice, overcome the curse of dimensionality. But our previous results don't guarantee this mathematically. So can we rigorously prove this? Fortunately, the answer is again yes. To prove this, we looked at a class called linear Kolmogorov PDEs with solution U. So they look like this. So this is the Hessian. So it's basically your second derivative. So this is some diffusion component. This is your gradient. So it's some advection component. And examples are the high dimensional heat equation and also this Black-Scholes equation from mathematical finance. So again, we want to prove existence, stability, and generalization as before. Let me have a look at time. Okay, 7 more minutes. So what we then use is a connection between this Kolmogorov PDE and an Ito diffusion stochastic differential equation. In case you're not familiar with stochastic differential equations, it's not very important. It's basically some randomized version of a differential equation. So an Ito diffusion has the following form, and then there is some very long formula related to this, something called the generator of this Ito diffusion. And then there is this cool representation formula called Dickens formula that says that if phi is your initial condition, and this one is C2 with bounded first partial derivatives, then it holds that U solves your Kolmogorov PDE. So this L is your PDE from before. And then this U can be defined in terms of your initial condition and then this generator of your SDE. So using this formula, we were able to prove the following theorem, namely that if we can approximate our initial condition phi without the curse of dimensionality, then there exist constants alpha and beta, such that for every accuracy epsilon and every input dimension d, you have some constant rho d that I'll explain later, and a 10-inch neural network with at most this many neurons, such that here your PDE residual is small, and here also this is the L2 error on the boundary. So this means that the boundary residual, so for the spatial boundary and the initial condition, will also be small. Then what do we observe? Our convergence rate, meaning this beta, is dimension independent. So that's already an improvement on our thing from before, because here, remember from the theorem, I'm not going to show it again, the convergence rate did depend on the dimension in a very bad way. The only bad thing that could happen is if our rho d, this constant, depends exponentially on d, because then we will still have a constant that grows exponentially in the dimension. And unfortunately, we were only able to prove that this rho d grows polynomially in d if mu and sigma are constant. So for instance, for the heat equation, but we couldn't prove it in the full generality. Okay. Then we could again prove very similar results as for the Navier-Stokes equation. So our second question is again, if we have a small pin residual, does this also imply a small L2 error? And the answer is yes. So in this case, we get this result. And then for the third question, if you have a small training error, does this imply a small generalization error? Then the question is again, yes, or at least sort of, because now we need to have random training sets. Because if you define a grid on a high dimensional space, you will inevitably run into the curse of dimensionality there. So you need to simulate random points in your high dimensional space, and then use some kind of Monte Carlo estimates. But of course, if you have a random training set, you can only prove bounds with a high probability. So in this case, we have with a high probability that the L2 error can be bounded in terms of the training error and then the training set sizes. And again, we get rates here, but this time they're different. You can see that now we need quite a lot of bounds for the boundary, for the spatial boundary, compared to for the initial interior domain, sorry. So that's again quite useful in practice. Okay, so then one could take this one step further even. So now we train neural networks for fixed initial condition, and then something one could also look at is deep operator learning. So then you actually map a function, an initial condition, to a solution to a PDE at a later time. But I will not really go further into this because I'm running out of time. Okay, let me quickly summarize my talk for you. So I talked to you about physics-informed neural networks, which can be used as surrogate models, meaning approximations to PDE solutions. And the cool thing is that you don't need any training data. So they're computationally very efficient. And then we presented some theoretical investigation by answering questions about the existence, stability, and generalization. And our results are valid for both low-dimensional PDEs and high-dimensional Kolmogorov PDEs. Okay, my voice is almost breaking down, so it's good that we're really at the end of the talk. Something I just wanted to mention, these are the relevant papers, but I guess the most interesting for you guys is this course. It's called Deep Learning in Scientific Computing. Since last year, it's taught every spring semester at ETH, mostly for mathematics and CSE master students, but also physics and engineering students are most welcome. And we teach stuff that's very similar to the theoretical results I provided in this talk, but also you will learn how to actually train these neural networks and obtain good approximations to the PDEs. Okay, and I think this is then the end of my talk. I thank you a lot for your attention. Um, Look, perfect timing. Um, okay, yeah. If there's any questions, I hope I can answer them in this way, or you can send me an email.
Yeah, so great. Thanks. I think it was a very good talk. It was very accessible, and he gave us a lot of insight into your research, so we can thank Tim for the brilliant talk, especially with his COVID. Right. Yeah, so as usual, we have the apéro in G69. Next week, there's no talk because of Easter break. And then the week after that, it's on the Wednesday, the 27th. It's in a different room because this room is occupied on a Wednesday. So it's G43. And yeah.